It's a pleasure for me being here today in this awesome room, and I'm also glad to talk you into our recent advance on research topic entitled UQ-based state-dependent framework for recovery and seismic risk assessment. In this session, I believe that everybody here is familiar with the peer probabilistic-based earthquake engineering framework. That basically we know that it is an holistic framework that assesses performances at a system level with respect to different decision variables such as monetary losses, fatalities, and so on and so forth. Basically, two axes define the, let me see if it works, yes. Two axes define the peer matrix, I would say, and are the first one related to the intensity of the seismic action together with its likelihood. On the other, instead, we have the performance levels of the structure that we can see, for example, depicted here on the left of the slides. And this results in a matrix that we can partition into two subdomains that are one that is allowed and the other one is not allowed. And here, what do stakeholders, engineers do is try to figure it out the perfect combination in order to comply with the performance objectives of the structures given the likelihood of the seismic inputs. And as a result, once we have done that, we know that we can use this matrix to derive seismic risk assessment in terms of damage, for example, experienced by the buildings or the system that we are studying, or in terms of dollars, meaning downtime, recovery time required by the structure to bounce back to a functionality level, or by means of death or casualties, fatalities. So this is something that is already widespread and well consolidated both in literature and also in practice. But what if we try to look beyond structural damage, so to how the system effectively bounce back and recover? So what if we are interested not only in the structural damage, but also on how, or better, what will happen next in the aftermath of the events? Or if we try to be more engineering sound, can we try to find a way to implement into this matrix, PRPB matrix, a curve like this, meaning a way to analytically connect time with recovery of functionality of a system? So can we do that in a seamless way in order to expand recovery also into the PRPB framework? This is our research question. And actually, recovery is not something new at all. We have seen that it's something that started already in the past, in the latest 90s, by American standards like the ATC, and then it has nowadays reached momentum again and a lot of attention since simulation or analytical functions start to pop out in order to estimate recovery time and to provide reliable statistics that do not depend only by empirical data, even if, to mention, there is a huge work related to the latest release of the ASUS database that provides us actually with new data and also expert opinions, again on trying to give us recovery time statistics, meaning how many days should I wait to reach again a damaged state level or a functionality level for my building. And this is usually an information that is provided both in terms of mean time or median time expressed in terms of days, or even better, I would say, in terms of recovery rates. So again, I will stress it out once more, is how can we use those information and try to integrate them into the framework of the PRPB that we have seen in the first slides. Well, why we want to do that? I would say that before starting something like that, we have to reason on how and why the PRPB framework is so popular and is also so much consolidate into everyday practice? Well, the basics or the underlying assumption is that at the end of the day, we are modeling both the seismic load and the structural response as a post-Sonian events. And this bring with us four underlying assumptions that are, first of all, we need to assume temporal independence of events and also stationarity of the hazard rate, meaning that hazard is constant through times. And most of all, those two hypotheses are very strong in the peer PV framework that are memoryless property, meaning I'm just interested on which is the state right now of my structure. I'm not interested in how my system evolve or reach that state. I'm just looking at the present moment, not at the whole history. And the other one assumption that is crucial, I would say, is that for peer PV framework, we assume that we have a renewability of the system, meaning that structure, for example, subject to extreme events such as collapse or severe functional loss, do not return to the original state after failure. Instead, they require measure retrofitting, I would say, or replacement, which fundamentally alters the physical and performance characteristics of the structure. Let's just think about cultural heritage systems or special infrastructures. Once they reach collapse or they accumulate too much collapse, well, the system has changed its nature, cannot be just considered as it was before without change their dynamic. And so, reasoning on that assumption lead us to what if we try to remove this assumption, so to consider that the dynamics of the problem changes. Well, basically, we have just kept alive the three underlying assumptions, but in that way, we reach a more general framework that are Markovian processes that can include in their self the Poisson processes. And this is pretty convenient, I would say, because it is not only well established in other sectors, especially in reliability engineering, but especially because it allows us to define this P vector, that is the probability to write down the probability along time on how my system, the state of the system changes with times, meaning what is the probability of being at damage state 0, 1 or 2 given time. I can now describe with a Markov process this change probability along the axis, the time axis. And this is pretty convenient, also provides us a closed form solution because it ends up in writing down this first order equation, derivative equation, and that we know as closed form solution given certain damage initial condition. So the problem becomes, okay, we want to write down this equation, so it will pop back, sorry. So to write down this equation, the key terms becomes write down this Q matrix that has a strong physical meaning because it is a collection of the rate of transitioning, meaning, for example, here we have damage state 0, damage state 1 and 2 that could be related to pristine structure, slight damage structure, or collapse structure. So in this metric, we just pop in the rate of transition, so the probability of passing by damage state 0, for example, to a more severe damage state. So the rows describe the initial damage conditions and the columns describe the arrival damage state conditions. And if we think about, again, the physical meaning, we know that if we think about passing through a more severe damage state, we are, in a way, considering an earthquake damage rate. Instead, if we try to, so we are describing the upper triangular part of the matrix. Instead, if we think on how the system can bounce back, so how the system can heal, we are writing down the transition rate, so how many times in a given window of time my system is going to be able to pass by from a damage, for example, state 2 to a damage state 0. And this, again, we can see it's still strictly related to the peer framework. It's not something new, because those rates are exactly something we are familiar with, and in the next presentation, I think somebody is going to cover it. here we are defining the fragility functions, specifically state-dependent fragility functions, meaning we are evaluating the probability of exceeding damage state threshold given an intensity measure, but not only that, also in initial damage conditions. So standard fragility functions are the first row of this matrix. Here we are also interested in the state-dependent version, so also in what happens if my structure has already experienced damage. And I just put here a QR code that refers to a previous work of me and my colleagues that focus on retrieving those state-dependent fragility functions, leveraging surrogate modeling and experimental real data. So to wrap up a little bit all that we have seen here, I would like to show you, for example, a benchmark case study. So we have understand that to know how the probability of being in different damage states evolve with time is a matter of resolving an ordinary differential equation, very simple one. But the ingredients are, again, defining this transition state matrix and assign a seismic hazard. So here, the structure that we are referring to is an industrial mock-up that we tested in true scale by means of shake table test at the center in Pavia. And here I've just reported the state-dependent diagram, meaning we consider just 3 damage states that are associated to the max drift ratio that my system can experience. So, as you can see, once, for example, we reach a threshold related to the maximum displacement of the structure that reaches collapse, the limit state, as we define here, we can no more heal it back, so we cannot recover it. So the only recovery, for simplicity here, is the one from damage state 1 to have again a pristine structure 2, so meaning from 1 to damage state 1 to damage state 0. And here you see a plot, just to have in mind that here what we are representing is the upper triangular part of the matrix, so the seismic damage matrix. So here we have our state-dependent fragilities. With a caveat, here we see the probability of being damage state 1, given that we start from damage state 0. Usually for us it's more common to see those shapes because this is of the probability of overpassing the threshold, not of staying in a certain damage state, just to point it out. And here, for simplicity, we just selected 3 hazard levels, so stationary input, and those data were retrieved by the ENGV database, and we can see a low to high seismicity intensity that we are going to use to our benchmark case. And here you can see as a preliminary result, so with a fixed recovery rate, the probability distribution for 3 cases. So probability of being damage state 0, you see it decreases with time, no matter the recovery strategies that we adopt, and also probability of being in damage state 1 and in damage state 2. You see it in 3 different scenarios, so low seismicity, medium, and high seismicity. And then you can see also this X that crosses just the moment in which, so the here, in which we have equal probability, not equal, sorry, in which we have the damage state, the probability of being damage state 2 that encounters the probability of being damage state 0, meaning that we are going to face collapse, so no matter how fast we can heal the structure. So to summarize and being on time, I just show you in this presentation very quick a recovery away PB version of the framework, of the peer PB framework that allows us to compute both for damage and recovery times, combined with what it is, those Markovian process in order to deal with recovery and also to state-dependent fragility functions. For sure, there are many open challenges. For example, one that I mentioned is the effects of recovery. So how does this change my probability, my evolving probability with time? And just to close this presentation, I would like to thank my colleagues that are Professor Bruno Soudré, Professor Bursi, Marelli, and Professor Broccardo. If you have any question, I'm very happy to try to respond.